Hey, welcome to episode 8 of Science Setup. This one we're going to start digging into shock absorbers, also known as dampers. This is going to be a multi-part series. So part 1, we're going to look at the shocks themselves and what makes them work. So first off, let's get through some terminology and the basic operation of shocks and what makes them work. So first thing is a shock absorber does not produce any force whatsoever unless it's moving. So in this picture here, this cutaway, the shock is sitting stationary. It is not moving at all. All the pressures in all the chambers are exactly equal, and the net force out of the shock is 0. So what we can go through here first is some names of the different chambers. So this is a bladder shock that I've got shown here. So there's 3 chambers in a bladder shock. There's an air chamber, what's called a compression chamber, which is above the piston, and a rebound chamber, which is below the piston. What separates the compression and rebound chambers is the piston with the holes in it. And what separates the oil from the air chamber is a little bladder that seals the oil from and prevents the oil from getting into the air chamber. So the first thing to understand is really the reason for the air chamber in a bladder shock. So any shock where you don't have the shaft extending all the way through, there is a volume change that occurs because of the shock shaft. As the shock compresses, the shock shaft takes up more and more volume of the space that we have available. And if we don't have some way of compensating for that additional volume that the shock shaft is occupying, the shock is just going to lock up solid because there's no place for the oil that the shaft is displacing to go. So in a bladder shock, that volume compensation is provided by this air chamber. In an emulsion shock, the volume compensation is provided by the fact that there's air bubbles in the oil that are formed because of pressure changes within the oil. And we'll explain that a little bit more in a minute. So if we don't have any volume compensation, what will happen is the shock will just lock up. You will not be able to compress it at all. And if you don't resolve that problem and you put your vehicle on the track with it in that condition, the first time it lands off a jump or hits a bump or anything like that, very good chance you're going to blow the seals out of your shock, or there will be some other catastrophic failure as a result of the shock being hydrolocked. So to compensate for that in the bladder shock, what happens is as you compress the shock, as the shock is compressed, the shaft, you can see here there's much more volume here of the shaft in this position than there is when the shock is fully extended. There's only a little bit of the shock shaft that's displacing oil here, and there's quite a bit of shock shaft displacing oil here. So what happens is the air pocket that we have above the oil compresses and the bladder deflects, and this is what gives you that volume compensation. When the shock is extending or rebounding, the opposite happens. The volume of the chamber here increases to fill the space that the shock shaft is no longer occupying. So that's how it works in a bladder shock. In an emulsion shock, you don't have this airspace. This airspace is not here. So how do we manage to accommodate this volume change without any sort of an airspace? Well, what happens is the silicone oil that we use in our shocks Little do you know that that silicone oil can have up to 20% air entrained inside of the oil. Now you can't see the air because it is completely dissolved in the oil, but it is there, and it's actually occupies space in between the silicone the silicone molecules. So you can't see it. What happens is when the air pressure or the pressure of the oil drops below what would be room pressure, is the oil can't contain the air, all the air in it anymore, so the air starts to bubble out. So if you've ever seen somebody using a shock pump, and you'll see them, they'll keep pumping it, and you'll keep getting air bubbles coming out of the oil. They seem to be forming out of nowhere. And essentially what that is that the air that's entrained in the solution in the silicone oil is actually coming out of solution. So that's how an emulsion shock works. It uses that entrained air, and by usually the first thing you do when you build an emulsion shock is you pump it a whole bunch of times. And by pumping it, you're encouraging that air to come out of the solution. So now you have that emulsion that makes that shock work. If you don't have any air in that emulsion or in that oil, you will have a shock that'll just hydrolock. So whatever you do, don't pump all the air out of your oil using a shock pump, because that's going to probably end with some disastrous results. So what happens now that we've got this emulsion in the oil is when the shock compresses, those bubbles can compress. So we've essentially taken what is considered an incompressible fluid, like water or oil of any nature. You can't compress it. Doesn't matter how much you push on it. It's going to keep the same volume. And we've introduced air into it, which now allows it to be compressed. So that's what allows the shock or the shaft volume to be compensated for, is by the bubbles in the emulsion expanding and contracting. So how does the shock develop the force? Well, when the shock begins to move, you end up with different pressures on either side of the piston. You need the different pressure because you've got to be able to force that fluid, the oil, through the holes that are in the piston to get from one side to the other. So as you are compressing, or moving the shock in the compression direction, or the bump direction as it's also called, the pressure in the compression chamber is higher than the pressure in the low side on the rebound chamber. So the oil is flowing from the high pressure to the low pressure side. In extension or rebound, the opposite happens. So now you have high pressure on the rebound chamber side and low pressure on the compression chamber side. So that forces the oil to go from the rebound chamber into the compression chamber. Now, something worth noting here is that the area that pressure acts on is different between the compression and the rebound side of the piston. So on the compression side, the pressure can act over the full surface area of the piston. On the rebound side, it only acts on the area that isn't occupied by the shock shaft. So what that means is the shock will produce more force in the compression direction or in the bump direction than it will in the extension direction because of this area difference. Now you'd think that area difference might be quite large, but actually it's not that big. For a 11 millimeter touring car shock, the difference in that area is about 8%. For a buggy or truggy, a 16 millimeter shock, that area difference is about 5%. So just purely on the basis of the area of the piston, the shock will develop that much difference in damping force in one direction versus the other, just purely because of the area difference. Okay, the other thing that is worth noting here is the faster the piston moves, the more force it develops. And the reason that is because the faster the piston moves, the more volume of fluid, the more fluid you've got to move from one chamber to the other in a shorter period of time. And the only way you can do that is that if you have a higher pressure difference between the upper chamber and the lower chamber. So in short, the faster the piston moves, the higher the pressure difference across the piston is, and the more force, the more damping force that the piston will generate. So that's why a shock absorber has a increase in the amount of damping as the velocity increases. Okay, so now let's talk about piston holes. Piston holes are the way one of the ways, we also can change the viscosity of the oil, but one of the ways that we can control the amount and adjust the amount of damping that we have produced by the shock. So I'm going to open up RC Crew Chief here and just show you something quickly. If you are following along, select the four-wheel drive truggy and then just select the damping tab, and we're going to go to the damping ratio tab, not the dynamic response. So one thing I want to show is that the hole diameter affects how much damping you have. So what I'm going to do is I'm going to compare two pistons that have the same total area. So 3 holes 1.74 millimeters in diameter versus 5 holes 1.35 millimeters in diameter have essentially the same area. So if you just shift click or control click, you can select whatever number of pistons you want, and then you can click graph and you can see the results. So I've got this set just to do one viscosity range, so I'm just using 600 CST. So you can see here's the graph of the 3 by 1.74, and here's the graph of the 5 by 1.35. So you can see both of these have exactly the same or within reasonable values, have the same total area, but the one with the smaller holes produces higher damping force. This curve essentially shows, or this axis here is a damping ratio, which I'll explain a little more in a second. But in simple terms, the larger the damping ratio number is, the more damping force the shock is providing. So just remember, the simplest way to remember this is it takes more force, more pressure to force the fluid through smaller holes than it does through larger holes. So smaller holes will produce more damping than larger holes when you compare equal areas. Okay, the other thing that I want to show here is how the damping ratio changes between low and high speed damping. So you can get quite different characteristics between the force that the piston is developing over the entire velocity range, or the speed range, the piston speed range, depending on the size of the holes. So if we look at now these are not equal area. There's probably a 20 or 25% difference in the total area between these two. And if we graph these, you can see that the 3x1.74 has much lower damping initially, and then increases to provide almost the same damping as the 10x1.14 once you get out to the much higher velocity ranges. So we'll talk some more about this in the next episode, but I just want you to be aware of this, that you can create quite different damping characteristics just based on the size and number of holes that you're using. Okay, now I want to talk a little bit about this damping ratio that I just mentioned. So the damping ratio is really a simple way to represent how much damping you have built into your suspension. So what it is the damping ratio is the ratio of the actual damping that you have in your shock to what's called critical damping. So critical damping is the amount of damping required for the system to respond without any overshoot. So it does not oscillate. It just goes straight to where you want it to go in a fairly quick fashion and does not go into any oscillations. So that is how the damping ratio is calculated. It's just purely the damping coefficient for the shock that we are looking at. That takes into consideration the oil viscosity and the number of holes and all the different shock characteristics, the shock mounting angles, everything, to what is the critical damping value for the particular suspension that you have. So it's a very simple, easy way to look at it. If your damping ratio is 1, then you have what's called critically damped. So your response is going to be nice and smooth, and it's not going to be the speediest response, but it's going to get there in a very controlled fashion. There's 4 basic levels. So critically damped is 1. Zero damped is where the system would just completely oscillate forever. Not really something that's even possible to achieve in the real world, because that would mean there would be zero friction and everything, and nobody's figured out a way to do that yet. So it's just a reference point. So you can see here this blue line represents the zero damped system. What's more typical is what's called an underdamped system. So the green line here is the underdamped. So it goes very quickly, overshoots slightly, and comes back and settles in to the final position without too much drama. This is the sort of response that you're going to see in the handling range for touring cars and so on. An overdamped system will respond slower and take a longer time to get to where you want it to be, but it will get there eventually, and it provides quite a bit higher levels of damping than an underdamped system. So this is the kind of thing that you see either critically damped or overdamped is the kind of thing that you want in off-road applications, and in on-road applications you normally want something that's somewhat underdamped. Okay, last thing I want to talk about is how we can believe everything that I'm telling you. And how we can do that is, I'm sure you understand by now that in order to try and simulate a shock is a very difficult thing. I've been thinking about this for a long time, ever since I created RC Crew Chief, and hadn't been able to come up with a good, reliable way to create something that had any sort of confidence without having test data. So fortunately, there's a test engineer down in the States who is an RC geek like me, and wanted to learn more about shocks, and he created a shock dyno. and he was also very generous with his data and shared it with me. So we kind of worked together for quite a while to figure out how these little things worked. There is a website listed here where you can see all the results of his shock dyno testing. And if you have some time, I would strongly recommend you check it out because there's lots of good information there. So what is a shock dyno? So a shock dyno basically runs or cycles the shock through a range of speeds and strokes. You can set it to run to a peak speed of 200 millimeters per second at a stroke of 15 millimeters. And you can vary those parameters depending on how you set the dyno up. So what it allows you to do is measure the force that the shock develops and the stroke and the velocity. So what you see here is a graph, and on the y-axis we've got the force that the shock developed, and on the x-axis we've got the velocity that the shock was run at. So the blue line here shows the actual test data, and the red line here shows the model that's used in RC Crew Chief. So you can see the model's not perfect, but it's darn close. Actually shockingly close. I was quite surprised that we were able to get this thing as close as we have managed to do. So the models that are used in RC Crew Chief do represent the real world. And this is only one condition I'm showing here. The number of different configurations and tests, and we even did impact testing, and got very good correlation with the impact results as well. So I'm very confident that the numbers that you're going to see in RC Crew Chief are representative of what you're going to see on track. So that's it for this episode. For those of you who've been using me as a cure for insomnia, hopefully you're having a good night's sleep. So stay tuned. We'll be back in a few weeks with part 2, where we're going to start looking at how to apply this all this new shock knowledge to make our cars work even better.